who is PROTOS? We are a company specialized on developing software tools and domain-specific languages for embedded systems. Everything that helps you to work on a much higher level of abstraction and with much more automation. We also provide test tools for embedded systems, hardware, software loop test tooling, and so on. And we also have a strong focus on embedded software architecture that goes together very closely with development of languages for embedded systems. Who am I? I'm Thomas Schütz. I'm an aerospace engineer with a fable for embedded software architecture, tests, and tools. So what's the problem we want to solve with contract-based design? Imagine you have a pedestrian traffic light or a traffic light on a street, and in both directions you have green at the same time. So what happens? Probably car accidents, loss of life, and so on. So that's something we want to avoid at any cost. So how can we avoid situations like that in complex software and in complex systems? That's the main question. The first question we have to answer is how do we describe what we really want? So how do I describe this? I can use a textual requirement or a specification. For example, requirement 1, the 2 traffic lights must not be green at the same time. Okay, that's not very formal, and there might also be room for interpretation and so on. So that's the first question. The second question is, how do we prove that the system actually does what it's supposed to do and it does not what it's not supposed to do? So we can write tons of test cases, unit, integration, acceptance tests, hill, SIL, mill, whatever it is. The problem is the test cases themselves are, again, very complex pieces of software, especially on integration and system level. On a unit level, they are relatively simple, but on higher levels, they can get really, really complex with simulations and so on and so on. So on that level, we might have trouble to really prove that the system is not doing what it's not supposed to do by providing test cases. So testing helps, but the problem is that a lot of bugs are introduced in very early stages and they're found in very late stages. So that's another big problem. So we introduce the bugs early, but we detect or fix them very late in the process, even after the rollout, and that gets very expensive and also very dangerous if those are safety critical systems. So now imagine a following situation. You define what you want, and you have models or code that implements what you want. So that's the current situation. So now the idea is here to define a formal contract, a formal specification of what is allowed or what is forbidden. And now by some magical mechanism, we can prove that the models or the code actually fulfill the contract, that they hold the contract. This would be a very nice thing to have. And that's what contract-based design is essentially about. So we want to prove that the software really does what it's supposed to do. Let's start with the classic design by contract introduced by Bertrand Meyer. The contract allows a formal specification of interfaces for functions and classes and enables a formal or runtime verification. That's the idea here. It's been introduced by Bertrand Meyer. He designed the programming language Eiffel with built-in contracts, and you provide pre and post conditions, invariants, and side effects as contracts. Those define the semantics, so the meaning of the functions and the classes and what they're supposed to do or not supposed to do. And in some languages like ADA or Eiffel, ADA in the field of avionics, they have a support for contracts on that level, on class or function level. An example would be here, for example, something in C. C does not have a functionality for proving contracts, but you can program them, for example, with an assert. This function, the square root, for example, you can define an assert as a precondition. So x must be bigger or equal 0, because if not, the square root is not defined. Then you have a safe playground here. You can call the square root function without any trouble. Then the result is again asserted as a post condition. So the result must be bigger or equal 0. If not, you do not hold the contract. So that's your promise, and that's what you expect, and that's the promise you will deliver. So the problem with those contracts on this level is it only works for synchronous functions and classes on a unit level, on a class level, or a module level in C. It does not help with asynchronous and concurrent systems. For example, for integration or system level, they help, but yeah, they do not really help with the big problem, with the integration problems. They are very fine-grained, so it's a lot of effort to add contracts to every function. And those classical contracts do not have states, no history, no execution orders, or no timing. So all those, let's say, asynchronous things or state-based things, they cannot handle. So now we introduce contracts on a higher level. We use state machines as interface contracts. You can use them at any given point, at any given interface in your system. Usually not at all the levels or at all the interfaces, but more on strategic interfaces like external interfaces to other components and so on, or to surround your safety critical system part with contracts. So the idea is to use a state machine to define the interface contract. I give you an example in the language C. You can also use this on that level. For example, you have 6 functions your C module provides. It's an initialize, start, stop, function 1, 2, 3. And now if I ask you questions like, yeah, what do I do? What do I have to do before I am allowed to call function 1? Should I initialize? Should I call start? Or should I call start and then initialize? Or what happens if I call stop? Do I have to reinitialize? Or can I just call start again? So those questions cannot be answered because we only have the syntax of the API. We do not have any information about the allowed order of execution, about timing and things like that. But by providing an additional documentation in form of an interface contract as a state machine, now I can answer those questions. So for example, I first have to call initialize, then I have to call start, and now I'm allowed to call function 1, 2, 3. And if I call stop, I need to call start again, but I do not have to call initialize again. So now I can answer those questions from before with a very, very simple piece of documentation here. So that's the idea of an interface contract, and also can add timing constraints and so on to this contract. So now what happens is that in a normal C API, if I want to test all the possible orders of execution, only every call once, I already have 720 passes through my system, so 720 potential test cases I need to do. With an interface contract, I know I can only take these 6 passes, so I can test them completely. If I make a reset and call it again, the numbers are increasing very, very, very fast. With the interface contract, they increase much, much slower. So 720 test cases or test runs I could easily provide. Even the 300,000, I could generate test cases to test those completely. So that's the idea. So we'll get a massive reduction of execution passes or internal states by many orders of magnitude. And this enables much simpler systems and better testability, because you can get a complete path coverage for the things that are actually allowed. And it's a very effective way to specify your interfaces. The problem is that's only a documentation, but I need to prove that my software actually holds the contract. Because if I cannot prove it, I still need to run all the test cases. So now the next question is, how do I prove it? So what can I do with the contract? On which level can I work with the contract? The first thing I can do with the contract, I can generate a consistent documentation directly from the contract. So that's very important, because we know systems, there are, let's say, 6,000 pages of internet interface specifications and contracts. If you do this manually, there will be many errors in the documentation alone. And it's a lot of work to produce this documentation. So it's much easier to generate consistent documentation from a contract. So if I go further on in the V model, so specification, next thing would be the modeling. If you have a model, a formal model of your software and generate the code, for example, from this model, you can do formal verification in the design phase. So you do not even have to run the system to prove that it's correct or not correct, at least according to the contract. It's also not 100%, but you get a formal proof that the contract is correct or not in your software. So that's the formal verification. The problem here is you need tools for that. So you need a modeling tool and a method that actually enables contracts. So there are not many tools out there that actually can do this in real world projects. We have such a tool, but yeah, I'll show this later. The next step in the V model would be to use the contract to generate test cases. So you take the contract and you generate test cases to prove that all the paths are correct or not correct. You try to break your system by generating test cases. And the last, and in some cases the most effective way, is to use the contract to generate a robust interfaces or monitoring interfaces for runtime verification. So you generate a piece of code between two interfaces, and we make sure that every call into this interfaces, so both directions if you want, is correct according to the contract. If not, we can filter it out, or we can throw an error or whatever it is. So basically it's the idea to make unbreakable interfaces. This helps not only with safety, but also with security a lot. So now let's give some examples for those contracts. First step is the model verification. We have a method called ROOM, real-time object-oriented modeling. It's actually a method from the domain of telecommunication. We use this a lot for embedded system with code generators and so on and so on. And in this method, we have added a contract, so you can specify the contract for every interface. Then during modeling time, we can prove that the contract holds in the model, and we can actually also use the assistant, modeling assistant, to fix the problems in the model. That's the model level verification, so model verification. The next thing would be contract as a black box test. We use this in combinatorial state transition tests for software and hardware in the loop tests. We have a little test system. It's called Minihill, and in this Minihill you can define state machines or contracts, state machine contracts, as a black box specification for all allowed or forbidden passes through your application. So for a component or for a part of your system, or even for the complete system. And from there we generate for all the passes needed to cover those scenarios, we generate test cases and by that providing combinatorial test case execution. So formal description for the black box behavior and the test case generation for path and data combinations. That's the second example. And we use this in our hardware-in-the-loop test system, Minihill. That's the smallest possible hardware-in-the-loop test system you can imagine. And we use those tests a lot to run robustness tests, safety critical tests, and so on. The third demo will be an interface definition language with contracts and generated runtime monitoring. So now during runtime, so you define the contract, you generate the interface, including the monitor. So the purple things here are generated. And now if the client calls, for example, a service implementation, it only calls it through the implementation of the contract, and the contract makes sure that it always works, or it never calls something that's not supposed to be called at this point in time. And in the end, you get a specification of what happened, or logging of what actually happened if an error occurs. So now to the live demos, I'm going to show you 3 demos. The first demo would be the model level contract verification. So in Room, you have components with ports. So now I have a little component here. It's containing a state machine. And in the state machine, I want to control a motor. To control the motor, I need 2 protocols. I need 2 interface descriptions. One is the motor control interface. So those are the messages I can send. I can start the motor, I can stop the motor, and as an answer, I get a done move to position and a stopped. So that's the syntax specification of this asynchronous interface. Now to the semantics, that's basically a state machine here. And if I start move to position, then I expect either a done move to position from the component that does what it's supposed to do, or I can also stop it while it's moving. In that case, I expect as an answer a stopped from the motor controller, for example. So that's the specification. And now let's use those interfaces. Oh, by the way, I also have for the timer. Timer are very, very huge source of race conditions, of course, sporadic errors, etc. So if I start a timeout, either I have to consume the timeout that's triggered, or I have to kill the timeout. So that's the semantic for the timeout. So now let's in the state machine. Now I'm going to add, let's say, a motor start. I want to start the motor to position 1, 2, 3. Okay. Now I started the motor, and now I could stop the motor. That's optional here, but I need to implement a transition that reacts on done move to position, because I've defined it so in my contract. So now I'm clicking this done move to position, and now I have a correct implementation. Now the next step would be, for example, let's state I'm done here. I'm in position now. That's correct. Now let's add, as good developers, we add a timeout, because this might probably fail. So I'm going to start a timeout. Let's give it 1,000 milliseconds. Now I start a timeout to make sure that if the motor does not move to the right position, I get a timeout. Now suddenly I have 2 transitions here I need to implement. I need to implement the timeout here. So now I have the timeout, because if the timeout fires, the motor did not do his job. But now you can see the motor is still running. So I need to either react on done move to position, or I need to stop the motor. In this case, I want to stop the motor. I want to stop the motor. And now I need to wait for the stopped motor because I need to evaluate whether it is really stopped or not. So that's what I have to do. And here you can see if the behavior is acting correctly, if the motor is acting correctly, I still have the problem that the timeout is still running. This might produce future race conditions or unknown situation, hidden links, and so on. So I need to either kill the timeout or implement the timeout tick here. In this case, because everything is okay, I'm going to kill the timeout, and now I'm correct again. Oh, sorry, I got the wrong timeout here. As you can see, we can, even with such a simple example, you can do a lot of just a second here, kill timeout. Okay, now it's done. Now it's correct. And in many cases, you can imagine now you want to add a new functionality. So let's say in start motor, you want to go another path. Now make something wrong, or also want to add a new functionality. And now I'm going to take this path, and suddenly I get the information that the motor is still running and the timeout is still running. So either I start whatever I want to do before I start the motor, or I need to handle those two interfaces. So that's the formal specification and the formal verification based on this modeling language. And now you can generate the code in C, C++, or Java, for example, to really implement the state machine. And you can be pretty sure that the implementation is really robust against race conditions according to the contracts. Of course, you have to do the contracts correct, but the contract is much, much simpler than the implementation of your functionality. That's a very important thing. So if the contract gets too complex, you run into a problem, but usually the contract is much simpler. So now the next level would be the test level. So let's have a look at a contract for generating test cases. So the idea here with a state transition test is that you define a state transition diagram, not for your implementation of your state machine in your system under test, but that's the black box description for your test cases. So every path from initial to end is a potential test case. So yeah, you need to configure variant 1, variant 1, then you need to test for certain different speeds and so on and so on. So you need to take every path to actually completely cover all the paths, potential paths in your system. Of course, you need to stop the proving with some metrics, because if not, it gets endless. That's it explodes. So that's not what we want. So now that's the definition of your test case. And now I'm going to generate the test cases needed. So that's the very compact contract again that defines what I want to test. And now here, that's those are the generate test cases with all the paths needed to cover the coverage defined in your test cases. So then now let's add some more variants. So let's add a variant 3, 4, 5, 3, 4, 5. So some more variants. Of course, you need to implement this here for the test case. Then I want not only to make some equivalency classes, but maybe some boundary values as well. So let's add the 1 and the 99 to have some useful boundary values here, or 100 and 0 if you want. You can see more variants, more speeds to test. Maybe I can add here some more. I want from brake, I want to go back, for example, to motor running, maybe. This might also be a test case. Now I added this here. So, and now I'm going to generate the test cases again, and let's see what happens now. I didn't even change any test steps. I only changed the order of the test cases and the high level specification. And suddenly we have something around 48 test cases with all the paths needed to cover those scenarios. Now, if I want to really find race conditions, sporadic errors, I can, for example, add a new metric, the end-switch metric, and I set it from 1 for a low combinatoric to, let's say, 3, 4, or 5. Let's take 3 for now. And now I generate many, many more paths through my system, which results, of course, in many more test cases. Let's update this specification here again. And now I have, I don't know, a couple of 100 test cases here. That's only the documentation. We also generate the test cases in C, and that you can directly execute them as hardware in the loop or software in the loop tests. So that's an example for contracts for test case generation. And now the third contract, you remember, first step was documentation. Second possibility was formal verification. Third possibility in a model. Third possibility was generation of test cases. And now the fourth possibility you have with those contracts is to generate runtime monitoring, to prove during runtime that your software is actually working correct. Why do I want to do this? In many cases, you do not have the modeling tools to actually prove things during modeling time. If you could generate test cases for those systems, but the problem is if somebody else is using your interfaces, for example, you're providing a piece of machinery with external interfaces, or you're providing a middleware for avionics, for example, you do not know now who is going to use or misuse your interface in the future. So you want to make it bulletproof in case somebody else is using the interface, or to make your software robust. So in that case, we can, for example, define an interface contract. We define with an interface definition language. We define the syntax of an interface, including already the values allowed, the range of values, the order of values, and so on. So those are the simple contracts, the interface contracts, but you also can define an interface contract as a state machine. So that's the interface state machine here. And now I can modify this, I can add more transitions and so on. So you see it's changing directly in the diagram. That's only for specification purposes. And now I can start to program my software, and the part of my software, the implementation of, so the interface descriptions, so interface definitions, for example, the service here, initialize, start processing, and so on. That's exactly what we've seen before. And also the interface contract, they are generated completely automatically. In this case, that's really an implementation of a state machine at your interfaces that listens at your interfaces and makes sure that nothing goes in or out that's not allowed. So, and in the end, I only have to implement the implementation itself and the caller, of course. So in this case, for example, the main program calls a valid sequence here. And now I'm going to run the program, and I get the information that everything's okay. So I have a valid sequence here. Now, as a programmer, I want to change something. So for example, I want to initialize after start processing, and I want to call the handle before I start processing, and so on. So now I'm doing some changes, and after every change, I can run my program. And now I get directly the information during runtime that my contract does not hold against my specification, or my implementation does not hold the contract. In this case, I get 2 errors. But now in a complex software, it's hard to find the problem. That's why we generate log files. In this case, the log file gives me a sequence diagram that shows me exactly in which interface state which call caused an error. So in this case, in the init, I call initialize, then I'm in the init state and I call a handle. Well, let's have a look. I'm call initialize and I call this handle. So that's the culprit here. Let's run this again. Now I fixed the problem. Now this problem is fixed. Now in processing, after start processing, I call initialize. Let's do this. I start processing. Here I call initialize. Now let's run this again. And here you see now we have valid sequences again, and my contract is okay. So that's also something you can give to the user of your interface to show him what he actually did wrong. That's a very, very nice piece of documentation of runtime logging that leads the programmer of the wrong interface directly to what he did wrong. That's very, very helpful. He will not be angry with you about this. Okay, so those are the three examples for contracts. Now, to sum it up, what are the typical use cases for contracts? You can protect your system at the external interfaces, for example, by generating interface monitors. That's a very, very common use case for contracts to make runtime verification. So, for example, if you have an incorrect behavior of other systems using your own system, or also user behavior, graphical user interface, that's also a very typical use case for contracts to make interfaces bulletproof, or also attacks, so safety and security topics. Then you can also implement complex behavior and fast and correctly. That's something where the model verification, model level verification, and the implementation assistant in combination with code generation helps a lot. So while you're working, it's checked all the time. Whatever you do, it's checked all the time during the modeling against the contract. Then you can also use this to generate redundant and diverse implementations of safety monitors. So if you have a safety critical system, you might need a redundant or even a diverse implementation for your safety monitoring. And you can specify the safety rules and generate runtime monitors or model verification or whatever it is with the contracts. And then in the end, you also can find bugs that are hard to find. So for example, sporadic race conditions, problems that happen once a year in one application and one customer side. So those are problems that are really, really hard to find and debug. So you specify the expected behavior and generate test combinatorial test cases to prove that or to find sporadic errors, to prove your system for robustness. And of course, there are many, many other use cases for contracts. If you have any questions about this, do not hesitate to contact me or Michael Weiss on Hitex side, or directly to me at PROTOS. I hope you enjoyed the webinar.